All right, I wanted to go over a little handout that I've written. We already did a video on the first part of this handout for line integrals. I typed everything up for you, so I'll just scroll through that. I've added a second page with surface integrals, and I just wanted to briefly work through those and then show you some key ideas at the end. So keep in mind we started out by looking at the integral that gives us the surface area of a given surface, and so I didn't write down all the details just to make this little handout a little more readable, but of course I'm assuming my surface S is parameterized by some R of U and V. And so if you want to get the area, you just integrate the length of RU cross RV over D, where D is the region that U and V are coming from. And then how do you do surface integrals of scalar functions? F of the parameterization times the length of the right derivative. Notice that's exactly how we did line integrals of scalar functions. F of the parameterization times the length of the right derivative. So really, really similar ideas here if you can see the patterns. How do you do surface integrals of vector functions? Very similar. You plug in the parameterization into your vector field F, and then you dot with no longer the length of the derivative, but just the derivative itself, which in this case is RU cross RV. A couple of things. So if you're integrating a surface integral and the vector field that you want to integrate happens to be the curl of something, then it's two things to think about. So first off, let's look at the corollary. Ask yourself, is the surface closed? And if the surface is closed and you want to take the surface integral of the curl, then you know you're going to get 0. And this is actually coming from the divergence theorem, but still, when you're thinking about surface integrals, you see curl there. First thing, ask yourself, is S closed? If it is, I'm done. The answer is 0. If it's not closed, ask yourself what its boundary curve looks like. And if it just has this one boundary curve, simple, closed, piecewise smooth, positively oriented boundary curve, then you can use Stokes Theorem and you can switch the surface integral of the curl of F to the line integral of F itself. But you just have to watch the orientation of everything, right? If your surface maybe looks like that, here's your boundary curve. If the surface is oriented up, then the curve has to be oriented counterclockwise around that up direction, whatever up direction the surface has. So Stokes Theorem. The divergence theorem is when you have a surface integral of not the curl of something, but just a vector field itself. You're allowed to go ahead and switch it to a triple integral and just take the divergence. And depending on the setup, again, going from here to there or vice versa may be more useful depending on what you're doing. So I've posted this handout to Teams. I hope it's helpful. You're welcome to use it on your final project, which I'll have more information on soon. Let's end this video looking briefly at all the different key integration theorems. And I just want to highlight in each case the idea of boundary. So for the fundamental theorem of calculus, we took an integral of a function. We wanted the area under our function little f. In this case, I guess big F prime is the notation that I picked. And I'm working over an interval of the x-axis. The theorem holds for an interval of the x-axis, and the fundamental theorem says, look, you can take this part over the whole interval, and you can switch it to this part, which is just the boundary of the interval. So you move from the whole interval to just the boundary. The fundamental theorem for line integrals says, hey, if you want to integrate this particular function over a curve like this, space curve, it suffices to just look at the endpoints. So these are very, very similar ideas. However, if you're willing to see it, the same idea carries on through the rest of the theorem. So Green's theorem says, hey, take a double integral of the right function over this region in the xy plane. So we're working over the whole region. And Green's theorem says, actually, you can switch it to just a line integral just over the boundary. So we're switching an integral over a whole region to just a statement involving the boundary curve. Stokes' theorem is very similar. You've got a surface integral of the curl of f over the whole surface. I've got this big loaf of bread looking surface here. And you can switch it to just the boundary. The boundary would be this bottom edge here. And actually, I said loaf of bread. That was really the wrong idea because it will give you the idea of a solid. This is not a solid. It's hollow. The bottom is open. It's like more like a clamshell maybe facing down. All right, so Stokes' theorem says you can take the whole surface and translate the problem to just the boundary curve. Again, orientation matters here, but I won't get into that. The divergence theorem says you can take a triple integral over the whole solid. This is the whole solid through this thing, right? And you can switch it to a surface integral over just the hollow boundary shell. So in every case, we're taking an original statement over a larger thing and translating it to a statement simply about its boundary. Boundary here is a surface. Boundary here is a curve. Boundary here is a curve. Boundary here and here are just endpoints, but it's the same fundamental notion. Well, that's it for today, and you've got some homework to keep you busy, and then we will have information. I'll have information to you about your final exam / final project shortly.